Today we're going to talk about Avocado. As I mentioned, the original presenter for this paper couldn't make it, and I learned this last minute, so I'm going to improvise a little bit. Avocado is, as the title implies, a secure in-memory distributed storage system, right? And by secure, what they mean is like it has to be tamper-proof, kind, right? So the problem that the authors are solving is like they compare it to a BFT to a degree, but I don't necessarily agree that this is a BFT problem. I think it does have slightly different properties, but you know, the idea is kind of similar that you know, if you deploy these protocols, if you deploy the replication protocols in the cloud, you know, in the public cloud, you kind of put in a lot of trust in the cloud provider itself, right? Obviously, the cloud provider, the engineers of the cloud provider can, you know, they have physical access to the machines. They can look at the data, at the code, at the processes, and you know, all of that stuff, the executables. So you do put quite a lot of trust into the cloud provider, right? And trust that the cloud provider has good enough security that all of the communication is secured, contained within the cloud provider, right? So it doesn't allow other maybe tenants to read the network, or other tenants to read the memory storage of your virtual machines that you're renting out and things like that. So obviously people are not comfortable with that, and I think a lot of the databases, they do provide like databases meant for the public cloud, they do provide ways to mitigate some of the issues described here, like encryption at rest, right? So the data can be encrypted when it's at rest, or the data can be encrypted, like the encrypted messages as well. So we can have some sort of protection by encryption, right? So there are systems that allow users to specify their own encryption keys, that are not known to the public cloud, to the provider. So at least you can kind of hopefully ensure that the data is not that the data cannot be read, right? And with the things like signatures and stuff like that, you can hopefully make the data tamper-proof. But there is another aspect of the security here that kind of goes beyond the data, right? So how do you ensure that your system is actually a system, that the system itself has not been tampered, right? So and this is kind of the Byzantine aspect that the paper refers to, that if you have a misbehaving system, you can solve it by a Byzantine fault tolerance protocol. If you have a misbehaving node, as long as you have like a certain threshold of nodes that are not playing by the protocol. So if the cloud provider has this absolute control over hardware, what does prevent them, for example, from changing your executable to a compromised one that may behave outside of the protocol, right? So that's not a good thing, and it's not so much about the executable too. It's the cloud provider, maybe they can tamper with the memory of this executable. So not even change the executable, but change the process itself, compromise the process that runs this database and whatnot. So this paper goes in and says, we want to build a secure system that is tamper-proof by the cloud provider, regardless of the privileges that the cloud provider has, or tenants of the cloud provider. So even if you have physical access to the hardware, even if you have maybe kernel level privileges at the operating system, or the hypervisor level privileges at the operating system, you should not be able to mess with the data and the actual replicated system itself. So the paper goes on and talks about this things called trusted executed environments, TEEs, right? So these are pretty much special features of the processors that restrict the access to the memory, even to the kernel, right, or hypervisor. So once you get into this restricted trusted execution environment, only the trusted code that's supposed to be there, that was verified, can execute, right? So, and no one outside of this trusted environment, not even the operating system kernel, at that point can do anything with that, with that memory and registers and stuff like that. So that's kind of like a protected local environment for you to run your code and ensure that the code is not tempered, right? That the memory that runs your code, all of the instructions and stuff, exactly the way they're supposed to be. So and this is what Avocado is doing. It's building the key value store that instead of running in the regular kind of user space in the regular environment, shared environment, as they say, they build the key value store that runs in the trusted execution environment. And that does have quite a few challenges. For one, in the architecture that they use, which is the Intel architecture, the trusted execution environment, or the enclave, it only has 128 megabytes of memory. They do say that it has paging capabilities, but it's very slow. So kind of you're limited to working with this 128 megs of memory for your for your code and for your storage. So obviously you cannot store a lot of things once if you're building a database. 128 megabytes is not enough. So another problem with this enclaves is they're not like they're meant for the local local execution, right? They're meant for one machine only. So how do you build a replicated system with this that runs on this trusted execution environment? Yeah, so the problem, so yeah, like replication for fault tolerance, that's what they need. Consistent, all of that stuff. Another problem that they face is this attestation mechanism, right? So in this enclave, trusted enclave, you have a mechanism to verify that it's not corrupt, essentially, right? So it's running what it's running. The memory is okay. So and you need to establish this kind of trust. And I think the mechanism that is used, like they described, the mechanism, it really requires, like it uses Intel, as the provider of the technology, as the source of trust here, in a sense. And they have to communicate with like Intel provided service to establish this attestation that the enclave is actually trusted. What's running there is correct. So that can be slow, and again, that's all geared towards kind of a single machine execution, right? So you do it on a machine, then stuff on this machine is correct. Stuff with the machine that's running in this enclave is correct. I'm grossly oversimplifying things, by the way. I'm not a security expert by any means. So yeah, I already mentioned that the memory is a limiting factor, paging is slow. And this is kind of their high-level architecture. They have to build their own trust system, right? So instead of relying on this single machine trust that's built by the Intel service, they build their own trust system, their own attestation system that is distributed, which still ultimately piggybacks of the Intel's servers, but in kind of hierarchical manner. So you need to establish this trust initially with the Intel service, the Intel attestation service IAS, and then you can use that as the source of trust to kind of build it, the nested levels of attestation within your system. They don't describe this in a honestly in a like very detailed way. So again, I'm like grossly oversimplifying. Replication layer. In this particular key value store, that's an ABD algorithm. So it does only put, gets, and deletes. It doesn't allow for more complicated APIs like scans, range operation and things like that. A networking layer in their system that's it's based on kernel bypass. It's using the ERPC framework that we already saw in one of the previous papers. And all of these three components, they run in this protected enclave, right? So the replication layer, the attestation service, networking layer, they are protected in this super protected memory, so that not even the administrators, not even kernel, no one can tamper with this memory, right? So it's kind of locked from being accessed outside of the process that actually runs in this enclave itself. So what they say is, because they build in the key value store, obviously the data, they want to make sure that the data is protected as well, but they cannot feed all of the data. So instead of trying to fit all of this data in 128 megs of protected memory, they only put the keys and some metadata, like the checksums and whatnot, in the memory, in the protected memory, and have a pointer to a shared unprotected host memory that will actually have the encrypted values, right? So obviously, someone can try to tamper with this, but that should be catched by metadata. So if there is a tampering with the actual values, which are encrypted, they're not in plain text, the metadata, the checksums and whatnot should be able to catch the fact that data was maybe replaced or tempered. So you should be aware that something is going on, and not serve this data essentially. So yeah, green stuff is this enclave, everything that's in the enclave, which is the all the code and the keys and the metadata for the storage. The actual data resides in the host memory, and so is the rest of the communication, like the network. Again, because they're using the kernel bypass, the send and receive buffers, they exist here. And the networking layer, the ERPC library exists in the enclave, but eventually, it kind of goes from this protected memory into the host memory. I think they call it the world change or something like that. So that's kind of a slow operation, but they designed this networking layer to have only kind of one change. Once it creates the packets, it just puts them in the buffers. I suspect that this is encrypted as well, so that once it's in a buffer, it's encrypted and signed. So it should be kind of tamper-proof anyway, and that's how it goes travels over the network. So the replication is rather boring. It's a ABD protocol, so nothing special there. I'm not going to focus too much on this, but ABD is very similar to what is being used in Apache Cassandra to a degree. It's kind of a two-phase protocol where the put operations require reads in the previous version, increments in the highest version read from the quorum, and writes in the new data with this incremented version, and reads a two-phase as well. You read from quorum. If quorum version doesn't match, then you pick the highest version and write it back. If it matches, then you can skip the write back phase, but in the most general sense, it's a two-phase operation. So yeah, this is how they orchestrate the key value store on a single machine. As I already mentioned, the data is not in the enclave, it's in the host memory. So in the protected memory, they only keep the information enough to point to the data where it sits, like the size of the data to read, the version, and the information that will be used to detect if something has been tampered, like if the data was replaced and whatnot. The actual data doesn't sit in this 128 megabytes of memory, so they can pack quite a lot of this tiny small keys and metadata and have a lot more actual data sitting outside of the enclave. And yeah, that's kind of very high level overview of what I want to say. As far as the evaluation, the interesting one, yeah, the interesting one here, figure 11, what was interesting to me, like in this particular figure is, so this native graph, it actually shows Avocado, the same algorithm implemented, but not in a secure memory, right? Not in this enclave. So just running in the regular memory space. So without running in this TEE, the thing is like twice as fast. So there is a substantial performance penalty for restricting yourself to this protected enclave. They did quite extensive evaluation actually of all the major components, like their attestation service. They evaluated this somewhere. They evaluated the single key value implementation that splits the keys and metadata in the enclave and the values outside. So they did quite a lot of evaluation of all the major components. Yeah, I think I'll stop at this point.